As you might have guessed it, there is another mode known as super or hypersynchronous operation, which necessitates the rotating magnetic fields to travel in opposite directions. As with our previous discussion, the rotor's physical position and electromagnet aren't tied together. Consider fixed frequency three-phase AC applied to the stator, such that the stator rotating magnetic field turns one full revolution clockwise. However, super slow frequency three-phase AC applied to the rotor such that it moves 30 degrees counterclockwise or negative 30 degrees in the same time period. Taken together, a quarter of the way through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor physical position is 7.5 degrees ahead. Halfway through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor physical position is now 15 degrees ahead. 3/4 of the way through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor's physical position is 22.5 degrees ahead. All the way through the cycle, both the rotor and stator magnetic fields made a full 360, but the rotor is physically 30 degrees ahead, such that it completes a full turn plus 30 every time the stator does a full 360. 12 full turns in the stator, and the rotor completes 13 turns in the same time period. See what happened? The rotor sped up. You might be tempted to rewrite the doubly fed induction motor rotor formula for hypersynchronous operation, but as long as you keep polarity in mind, our original formula will work quite well. Viewers will recall in the mechanical power lecture, we define clockwise as positive and counterclockwise as negative. As previously, what if we applied fixed frequency 60 Hz AC to a stator with 2 pole pairs per phase in the clockwise or positive direction, and super slow 1 Hz AC to the rotor in the opposite or counterclockwise direction? If you think about it, that's negative 1 Hz. An application of the doubly fed induction motor rotor speed formula demonstrates the rotor should move at 1830 RPM, 30 RPM faster than the regular synchronous speed for a 2 pole pair per phase motor at 60 Hz. Hence the title hypersynchronous. What if we kept 60 Hz AC applied to the stator in clockwise direction, ramped up excitation frequency to the rotor in the opposite direction in negative 1 Hz increments? Successive applications of the doubly fed induction motor rotor speed formula demonstrates the rotor should move at 1860, 1890, 1920 RPM, and so on, increasing in 30 RPM steps, each negative 1 Hz increment. If you think about it, given 2 magnetic fields revolving in opposite directions, the rotor is again responding to the resultant differential between them. In traditional synchronous operation with 60 Hz in the stator and pure 0 Hz DC on the rotor, it operates like a 2 pole pair per phase synchronous motor at 60 Hz. With 60 Hz in the stator and negative 1 Hz in the rotor, it operates like a 2 pole pair per phase synchronous motor operated at 60 minus -1 or 61 Hz. With 60 Hz in the stator and negative 2 Hz on the rotor going the opposite direction, it operates like a 2 pole pair per phase synchronous motor operated at 60 minus -2 or 62 Hz, and so on. Again, you might think of this in relative terms. Let's say a car traveling at 60 miles per hour passes another car traveling at 10 miles per hour in the opposite direction. Understandably, there'd be a 70 miles per hour differential between these two opposite moving cars, and so on. I must remind the viewer that regardless of the mode employed, traditional synchronous mode with fixed frequency 3-phase AC in the stator and 0 Hz DC on the rotor, hyposynchronous mode with fixed frequency 3-phase AC on the stator and variable frequency 3-phase AC on the rotor traveling in the same direction, or hypersynchronous mode with fixed frequency 3-phase AC on the stator and variable frequency 3-phase AC on the rotor traveling in the opposite directions, all of these are synchronous modes of operation, not induction, because the rotor electromagnet remains locked in with the stator rotating electromagnet despite the variability of the rotor's physical speed. Given this observation, hyposynchronous and hypersynchronous modes share characteristics identical to traditional synchronous operation with regard to field current and pull-out torque, line current, and reactive power requirements. Viewers will recall pull-out torque. The torque at which synchronous motor loses synchronization is roughly linearly dependent upon field current. As field current increases, so does pull-out torque until it reaches saturation, while pull-out torque eventually flatlines. Additionally, we learned by varying field current, one can also observe changes in line current and reactive power consumption for a given load condition. Under excitation of the rotor means the stator draws reactive power as would a inductive load. In contrast, overexcitation of the rotor means the stator supplies negative reactive power as would a capacitive load. A graph of reactive power as a function of field current looks something like this, which identifies an important operating point. At a given load condition, field current can be so managed that the motor neither draws nor supplies reactive power, and voltage and current are perfectly in phase with one another. This would be a case of unity power factor and minimum line current. Lastly, we learned that starting synchronous motors necessitating synchronization between the stator and rotor magnetic field isn't as easy as one might initially suspect, principally because upon the closure of a full voltage starter, the stator rotating magnetic field is instantaneously established at full speed, whereas the rotor and applied load with some level of static inertia may take some time to come up to this speed. For this reason, one might need to resort to some cunning trickery to either speed up the rotor or slow down the stator. We explored several synchronous motor starting methods in the Synchronous Motor Starters lecture, available at the Big Bad Tech channel. All these properties remain true for doubly fed induction motors in hyposynchronous and hypersynchronous operation, and I'll not repeat myself today. I will, however, take the time to caution you that in these modes you need to pay attention, because you're not supplying the rotor with DC anymore, but rather a variable frequency AC. This means you gotta watch out for frequency-dependent phenomena like inductive impedance. Viewers will recall inductive impedance magnitude Z sub L is equal to 2 pi FL. Gee, where have I heard that before? Oh yeah, I mentioned it like 6 minutes ago. Given low frequency AC, the inductive impedance will be low. At higher excitation frequencies, inductive impedance increases. This brings us back to how field current influences pull-out torque and reactive power requirements. Let's say you're rolling along in hyposynchronous operation with fixed frequency 3-phase AC on the stator and variable frequency 3-phase AC on the rotor traveling in the same direction, and you've adjusted field current magnitude properly for a specified desired pull-out torque, line current, and reactive power requirement at that particular rotor excitation frequency, but you want the rotor to turn slower. What are you going to do? The proper response would be to increase rotor excitation frequency. That is true, but it's only part of the answer. Think about what happens at increased frequency. Yes, with increased rotor excitation frequency, the differential between the stator and the rotor rotating magnetic fields will decrease, and yes, the rotor's rotational speed will slow down, but also think about what happens to the inductive impedance of the rotor windings. Given inductive impedance is a frequency-dependent phenomenon, impedance will also increase as a result of increased rotor excitation frequency. And if you're using a constant voltage source, field current will decrease because of increased impedance. If you keep raising rotor excitation frequencies in an effort to slow the rotor down, at a certain point, the inductive impedance of the rotor windings will be so high and the field current so low, the rotor will reach pull-out torque too early, lose synchronization, and everything will just all go to hell, and you will fail your motors and generators class, and your imaginary girlfriend will break up with you. The point is, the AC to AC converter on the rotor shouldn't be producing just variable frequency 3-phase AC, but rather variable frequency and variable magnitude 3-phase AC. At higher rotor excitation frequencies, the AC to AC converter also needs to step up voltage due to increased inductive impedance to keep field current constant. Since this is pretty important, this is perhaps worthy of a quick practical demonstration. Along the way, we'll demonstrate how the rotational speed of a doubly fed induction motor responds to different rotor excitation frequencies. Let's first get the motor rolling in traditional synchronous mode with pure DC on the rotor and fixed frequency AC on the stator. As can be expected for a traditional electrically excited synchronous motor with 2 pole pairs per phase at 60 Hz, the rotor turns at exactly 1800 RPM. If I lightly load the motor up with 0.5 Newton meters of counter torque, given this is synchronous operation, the rotor remains turning at exactly 1800 RPM. I adjust the exciter voltage until field current reaches around 400 milliamperes DC. In this perfectly power factor corrected state, the line current bottoms out at maybe 310 milliamperes AC on the stator, and the stator consumes roughly 113 watts of real electrical power and neither absorbs nor supplies any reactive power. If we're to highlight this operating point on the pull-out torque, line current, and reactive power requirements as a function of field current graphs, we'd be right here, i.e. where we want to be. Minimal line current, neither under nor over excited. Let's say I want to slow the rotor down. This is a perfect scenario for hyposynchronous operation. Instead of DC, I start supplying 2 Hz 3-phase AC to the rotor traveling in the same direction as the 60 Hz stator. The motor still exerts 0.5 Newton meters of counter torque, however slows down to 1740 RPM as we might expect. This being said, notice what happens to the rotor and stator electrical characteristics. Given I changed the frequency from 0 Hz to 2 Hz, but kept voltage magnitude the same, field current decreased from 400 milliamperes to 370 milliamperes because the frequency-dependent inductive impedance of the rotor went up. We've departed from our ideal operating point. As a result, line current rises and the motor starts drawing a small amount of reactive power. Let's say this is still too fast. I want to slow the rotor down. I ramp up rotor excitation frequency from 2 to 4 Hz, keeping voltage magnitude constant. The rotor slows down to 1680 RPM as we might expect. Again, notice what happened to rotor and stator electrical characteristics though. Given I increased the frequency, but inappropriately kept voltage magnitude constant, field current decreased because the frequency-dependent inductive impedance of the rotor went up. We've again further departed from our ideal operating point. As a result, line current rises and the motor starts drawing more reactive power. We are deep in underexcited territory now. You note every time field current decreased, not only did the line current and reactive power increase, resultant pullout torque decreased. We haven't reached it yet, but we are clearly playing with fire here. If I try to slow the rotor down even further by exciting the rotor to 6 Hz AC, everything goes to hell rather quickly. At 6 Hz, inductive impedance is so high and field current is so low, the magnetic fields lose synchronization, line current skyrockets, and the motor sounds as mad as a bobcat asked to fetch. Shut her down. Long story short, this is not the way to do this. The ADC to AC converter driving the rotor shouldn't be adjusting rotor excitation frequency, but also voltage. At low excitation frequencies, when rotor inductive impedance is low, keep voltage low. At higher excitation frequencies, when inductive impedance is higher, step voltage up so field current remains in the ideal zone for proper operation and pull-out torque. This is often known as a linear volts per hertz profile, in this case including a DC offset. At DC, apply a certain voltage to get the desired field current. At 2 Hz, when inductive impedance rises, step voltage up that same linear amount to keep field current relatively constant. At 4 Hz, when inductive impedance again rises, step voltage up that same linear amount to keep field current relatively constant, and so on. Here's a demonstration of this properly managed style of doubly fed induction motor speed control. As previously, I first get the motor rolling in a traditional synchronous mode with pure DC on the rotor and fixed frequency AC on the stator. As can be expected, the rotor turns exactly at 1800 RPM. Then lightly load the motor with 0.5 Newton meters of counter torque. Given this is synchronous operation, the rotor remains turning at exactly 1800 RPM. I adjust the exciter voltage until field current reaches around 400 milliamperes DC. In this perfectly power factor corrected state, the line current bottoms out and the stator consumes roughly 113 watts of real electrical power and neither absorbs nor supplies any reactive power. If we're to highlight this operating point in the pull-out torque, line current, and reactive power requirements as a function of field current graphs, we would be right here, where we want to be. Minimal line current and neither under nor overexcited. Let's say I want to slow the rotor down. Instead of DC, I start supplying 2 Hz AC to the rotor traveling in the same direction as a 60 Hz stator. The motor still exerts 0.5 Newton meters of counter torque and slows down to 1740 RPM as we might expect. This time, however, with a linear volts per hertz ratio, given slightly increased excitation frequency, voltage is also slightly increased and pretty much everything remains the same. Field current remains high, and as a result, line current remains at a minimum and the stator neither absorbs nor supplies any reactive power. By adjusting voltage in the same proportion as frequency, we're keeping field current where it needs to be, so this hyposynchronous motor remains inside that sweet spot. Let's perform the same speed ramp down by supplying progressively higher rotor excitation frequencies, only this time progressively increasing voltage magnitude as we do so. The idea is to keep field current, and thus line current and reactive power demands inside an ideal range. At an increased 4 Hz and a slightly increased voltage, the rotor slows down to 1680 RPM and field current remains high. Line current remains low and the stator neither absorbs nor supplies any reactive power. At an increased 6 Hz and slightly increased voltage, the rotor slows down to 1620 RPM and field current remains high and line current remains low and the stator neither absorbs nor supplies any reactive power. Check it out, we're still rolling at 6 Hz. Isn't that where it all went to hell last time? I think it was. At 6 Hz, we're rolling at 1620 RPM. We haven't reached pullout. Data for increased excitation frequencies beyond 6 Hz appears below. In each scenario, given we've adjusted voltage magnitude in the same proportion as frequency, field current remains high, line current remains low, we neither absorb nor supply reactive power, and importantly, we don't reach pullout torque. You get my point. This is the way you operate a doubly fed induction motor. To vary the resultant rotational speed of a doubly fed induction motor, not only must you supply the rotor with variable frequency three-phase AC, you must also supply it with variable voltage magnitude to account for frequency-dependent inductive impedance. As we wrap this demonstration up, it should be noted that rotor excitation frequency need to be applied in stepped exactly 1 Hz or 2 Hz increments, but changed in a continuously variable analog fashion so the rotor speed meets the exact needs of a specific application. Because that's what this is all about, right? Speed control. Now, some of you might be like, yeah, but why can't you just grab a regular induction motor and an off-the-shelf motor drive and control speed that way? Why'd you drag us through this admittedly cunning application if a motor drive and an induction motor could do the same thing and control speed? True, motor drives do allow speed control, but a doubly fed induction motor presents additional advantages beyond speed control, 3 of which immediately come to mind. Number 1, cost. Note a traditional motor drive must be sized to handle all of primary power, whereas the power electronics devices controlling a doubly fed induction motor only manipulate the smaller portion of rotor power. For this reason, an appropriately sized AC to AC converter on a doubly fed induction motor might be cheaper than a full-size motor drive. 2, it's synchronous. This is an often overlooked fact. Again, hypo and hypersynchronous modes are extensions of synchronous mode, and once rotational speed is established, the 2 electromagnets lock into each other, and as long as load torque remains below pullout, they remain at that specified speed. Induction motors, not so much, because they're known to exhibit variations in speed with changes in load torque. Additionally, while in operation at that desired stable speed, field current can be so managed that the motor neither supplies nor absorbs reactive power. And finally, and most importantly, number 3, it's really cool. Am I right? Check the box with the appropriate response. All right, that is that. In summary, hyposynchronous operation uses fixed frequency 3-phase AC on the stator and variable frequency and voltage 3-phase AC on the rotor traveling in the same direction. As rotor excitation frequency and voltages increase, the rotor slows down. As the name implies, hyposynchronous operation is below regular synchronous speed. Hypersynchronous operation is essentially the same thing, only the rotor rotating magnetic field goes in the opposite direction of the stator. As rotor excitation frequency and voltages increase, the rotor speeds up. As the name implies, hypersynchronous operation is above regular synchronous speed. Before bringing this lecture to a full close, allow me to revisit a point I made earlier in this lecture. I think one of the superpowers of engineers is their ability to call bull when they see it. The superpower, by the way, may be a very poor fit as an officer in the United States Army. The bullshit I'm calling is this. This is not a doubly fed induction motor. This is demonstrably an extension of synchronous mode. So why is it called a doubly fed induction motor? I genuinely don't know. I get the doubly fed part since you're feeding both the stator and rotor. And I obviously get the motor part since it's consuming electrical power and producing rotating mechanical power, my go-to definition of a motor. But induction? This is not induction. This is synchronous mode with all the benefits, i.e. constant speed inside its operational range and control of reactive power, and drawbacks, i.e. more complex starting circuits. So why is it called induction? Again, I don't know, but I can only surmise the clearly incorrect reason it is commonly referred to as such. Let's start with some basic definitions that I hold true so you can see where I'm coming from. What does induction imply? Induction implies that induction is happening. Induction is a changing magnetic field that sweeps through a conductive coil and generates voltage, which generates current, which generates an induced magnetic field, hence the name, which follows the original magnetic field that induced it around and around. Induction motors exhibit changing speed as a function of load torque. Induction only happens in traditional wound rotor induction mode with a cage-like induction rotor. What does synchronous imply? To me, synchronous implies 2 magnetic fields locked into one another that follow each other around and around. In traditional synchronous, hyposynchronous, and hypersynchronous, there are 2 magnetic fields locked into one another that follow each other around. Yes, you can vary the speed by adjusting the excitation frequency of the rotor, but once it's set at that speed, the speed should remain constant inside its operational range. So why is this called induction? Only way I can rationalize this clearly wrong title is because you're doubly feeding what wouldn't ordinarily be an induction motor to act synchronously. After all, a doubly fed induction motor acting synchronously is just a repurposed wound rotor induction motor. This would be like buying a Ford Pinto, only to replace the wheels, frame, engine, exhaust system, transmission, cooling, and exterior with entirely modern, high-power efficient components, yet still call it a Pinto because you kept the exploding gas tank. Doesn't mean it's right, but I kind of get where this might originate. All right, before I go off on some other tangent that winds me up, let's call it a day. In conclusion, this lecture examined how a wound rotor induction motor can be repurposed as a doubly fed induction motor. We took a look at synchronous, hyposynchronous, and hypersynchronous operation and explored how varying rotor excitation frequency one could control resultant rotational speed above and below what would ordinarily be considered synchronous speed. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.